All right, well, hi. This is my recording on a problem that we were working on after school, and the Doppler shift of mechanical waves versus electromagnetic waves. So let me try this out here. So the problem was that we had a car, and this is there's our car, and it was moving at some velocity v, and there was a radar gun, and the radar gun, there's my radar gun, sure, and it was sending out electromagnetic waves with, of course, the speed of light c. And the question is, if the waves go out to the car and reflect back, what is the frequency that the radar gun detects? And so we, as a group, the group that was after school, we're trying to apply Doppler shift twice, as in reflections. And so let's think of it this way. We know that first, we're going to have a received frequency from the car that's Doppler shifted. So the car is like acting like the receiver at first. And let's say that the frequency that the radar gun sends out is F. So the frequency that the car receives, well, it's going to act like a moving observer. And because it acts like a moving observer, what we can do is say that it's going to be equal to the frequency emitted by the radar gun. And again, because it is a moving observer, we're going to use C over C plus V here. We know it's going to be a decrease in perceived frequency at the car, and so it's going to be that. And this is our equation for moving observer. And then it's going to also reflect. So it's going to then reflect and be like a source now that's moving. So this is a moving observer. I'm just going to put, well, I'm not going to spell it all out, but moving, because I need a pen, but so this is a moving O. All right, now we have a moving source. And the source is moving away from the radar gun. The source now is the car that it reflects off of, so moving S. So now what the radar gun, the frequency that the radar gun, I'm going to put FG, perceives, is now this frequency. So this frequency is now shifted, F, C plus V. And that whole frequency is shifted. And we're now going to use the expression for the moving source. And it's going to be lower. So on the top, we want C minus V on the top over C on the bottom. And I hope you can see, hope you can see here that these are going to cancel out. So basically, what the gun perceives is going to be F times C minus V over C plus V. And we have not made any assumptions here about light, speed of light versus the speed of the car. And so you can see this is completely just the same as what we did for mechanical sound waves. So this is electromagnetic. So we're saying C is the speed that the wave is traveling. It's the speed of light. So now I'm going to calculate delta F. I'm going to calculate the shift in the frequency perceived by the Doppler gun. And so that's going to be its original frequency, F, minus this frequency here. So minus f times then c minus v over c plus v. Okay, so a few things that are going to make this mathematically easier for us. I'm going to write this as f, and I'm going to write this as c plus v over c plus v. That's the same thing as 1, right? And that's to give a common denominator from the two. Minus then f c minus v c plus v. So I hope you see where I'm going with this. So I'm going to pull out an f, and I get the following. So when I pull out the f from both, the common term of f, notice I get c plus v minus c, and then the minus minus v. So the c's are going to cancel, and I'm going to get 2v on the top. So I have 2v, and then on the bottom I have c plus v. So notice this is getting closer to where we were. So now we make the assumption that v is a lot smaller than c. And when we do that, then c plus v just practically is c on the bottom. So this is approximately equal to 2v over c times the original frequency of the Doppler gun f. And that again is the shift. So the specific question that Walden brought up, and that I think also Sahil had this question as well. So then the frequency as detected by the gun is then f minus 2v over c f, because it's going to be a shift downward. So the actual perceived frequency is going to be f minus 2v over c f. And here, the only assumption that we made here that's different than what you could do with a mechanical wave like sound is this. We assume that v is a lot smaller than c, and that would not necessarily be true for a sound wave. That is definitely true for a light wave. So that's where this approximation comes in. I hope this helps. I hope you feel like you understand it a little bit better. So this was the answer that we were trying to get in class. We conceptually thought through it. We understood the minus sign. We understood the reflection gave us the double speed, but then mathematically we couldn't make it make sense until I really sat down and thought through this algebraically and understood the assumption here. And the assumption is that with an electromagnetic wave, the speed of the car is going to be a lot less than the speed of light. And so that turned c plus v into just c, because when you add something really, really small to something's really large, it's just pretty much the thing that's large. And so that is our answer. So there you go. Hopefully this has made you less confused, and good luck on the test studying for your test tomorrow.